Up to now, we've talked about resistors and capacitors and other components, and we've connected them up and learned about Ohm's law for resistors, and we've learned some things about series resistors like we show here. The idea of Kirchhoff's laws, these are basically common sense laws that we can derive from looking at simple circuits, and in this video we're going to work out Kirchhoff's current law. Let's take a look at these series resistors here. There's a connection point right there, and that's called a node, a junction. And one of the things we know is that when we put current through this, let's say we put a current through here, and we know that current is flowing charge, so we know that the charge does not collect anywhere. So that means it comes out of this resistor and flows into the node and then goes across and it comes out on this side. All the current that comes in comes out. That's something we know. That's the conservation of charge, and we know that the charge does not pile up anywhere. We'll call this current I1, and we'll call this current I2. And we know we can just write right away I1 equals I2. That seems pretty clear from our argument about charge. Now let me add something else here. We'll add another resistor to our node, like that. And this now, there's going to be some current going this way. Let's call that I3. And now this doesn't work anymore. This I1 and I2 are not necessarily the same. But what we do know is any current that goes in has to come out of this node. So we can say that I1 equals I2 plus I3. That seems pretty reasonable. And in general, what we have here is if we take all the current flowing in, it equals all the current flowing out. And that's Kirchhoff's current law. That's one way to say it. In mathematical notation, we would say I in, the summation of currents going in. This is the summation sign, is the summation of I out. That's one expression of Kirchhoff's current law. So now I want to generalize. I want to generalize this a little bit. Let's say we have a node and we have some wires going into it. Here's some wires connected up to a node, and there's current going into each one. I'm going to define the current arrows. This looks a little odd, but it's okay to do. All going in. And what Kirchhoff's current law says is that the sum of the currents going into that node has to be equal to 0. Let's work out how that works. Let's say this is 1 amp, and this is 1 amp, and this is 1 amp. And the question is, what is this one? What's that current there? If I use my Kirchhoff's current law expressed this way, it says that 1 plus 1 plus 1 plus I, whatever this I here, has to equal 0. And what that says is that I equals minus 3. So that says minus 3 amps flowing in is the same exact thing as plus 3 amps flowing out. So 1 amp, 1 amp, 1 amp comes in, 3 amperes flows out. Another way we could do it, equally valid, this is just 3 ways to say exactly the same thing. I have a bunch of wires going to a junction like this, and this time I define the currents going out. Let's say I define them all going out. And the same thing works. Sum of the currents, this time going out, I'll go back over here, I'll write in, all the currents going in. That has to equal 0 as well. And you can do the same exercise. If I make all these 1 amp and ask, what is this one here? What is I here? Outgoing current, it's 1 plus 1 plus 1 plus 1. Those are the 4 that I know, and those are the ones going out. So what's the last one going out? It has to equal 0. The last one has to be minus 4 equals 0. So this is a current of minus 4 amperes. So that's the idea of Kirchhoff's current law. It's basically we reason through it from first principles because everything that comes in has to leave by some route. And when we talked about it that way, we ended up with this expression for Kirchhoff's current law. And we can come up with a slightly smaller mathematical expression if we say, let's define all the currents to be pointing in. Some of them may turn out to be negative, but then that's another way to write Kirchhoff's current law. And in the same way, if we define all the currents going out, and you actually have your choice of any of these three, anytime you want to use these, if we define them all going out, this is Kirchhoff's current law. And we'll use this all the time when we do circuit analysis. Now we're ready to start hooking up our components into circuits. And one of the two things that are going to be very useful to us are Kirchhoff's laws. And in this video, we're going to talk about Kirchhoff's voltage law. If we look at this circuit here, this is a voltage source. Let's just say this is 10 volts. And we'll put a resistor connected to it. And let's say the resistor is 200 ohms, just for something to talk about. One of the things I can do here is I can label this with voltages on the different nodes. Here's one node down here. I'm going to arbitrarily call this 0 volts. And then if I go through this voltage source, this node up here is going to be at 10 volts. 10 volts. So here's a little bit of jargon. We call this voltage here. The voltage goes up as we go through the voltage source, and that's called a voltage rise. And over on this side, if we were standing at this point in the circuit right here, and we went from this node down to this node, like that, the voltage would go from 10 volts down to 0 volts in this circuit. And that's called a voltage drop. That's just a little bit of slang or jargon that we use to talk about changes in voltage. Now I can make an observation about this. If I look at this voltage rise here, it's 10 volts, and if I look at that voltage drop, the drop is 10 volts. I can say the drop is 10 volts, or I could say the rise on this side is minus 10 volts. A rise of minus 10. These two expressions mean exactly the same thing. It meant that the voltage went from 10 volts to 0 volts, sort of going through this 200 ohm resistor. So I write a little expression for this, which is V rise minus V drop equals what? Equals 0. I went up 10 volts, back down 10 volts, I end up back at 0 volts, and that's this right here. And this is a form of Kirchhoff's voltage law. It says the voltage rises minus the voltage drops is equal to 0. So if we just plug our actual numbers in here, what we get is 10 minus 10 equals 0. I'm going to draw this circuit again. Let's draw another version of this circuit, and this time we'll have 2 resistors instead of 1. And we'll make it, we'll make it 2 100 ohm resistors. And let's go through and label these. This is again 10 volts. So this node is at 0 volts. This node is at 10 volts. What's this node? This node here is, these are equal resistors. So this is going to be at 5 volts. That's this node voltage here with respect to here. So that is 5 volts. This is 5 volts. And this is 10 volts. So let's just do our visit again. Let's start here and count the rises and drops. Okay, we go up 10 volts, then we have a voltage drop of 5, and we have another voltage drop of 5, and then we get back to 0. We can write the sum of the rises and the falls just like we did before. We can say 10 volts minus 5 equals 0. All right, so I can generalize this. We could say this in general. We can do the summation, that's the summation symbol, of the V rise minus the sum of the V fall equals 0. This is a form of Kirchhoff's voltage law. The sum of the voltage rises minus the sum of the voltage falls is always equal to 0. There's a more compact way to write this that I like better, and that is we start at this corner. We start at any corner of the circuit. Let's say we start here. We're going to go up 10 volts, down 5 volts, and down 5 volts. So what we're adding is the voltage rises. We're adding all the voltage rises. Rise plus 10, that's a rise of minus 5 and a rise of minus 5. So I can write this with just one summation symbol. The voltages around the loop, where I takes us all the way around the loop, equals 0. So this means I start any place on the circuit, go around in some direction, this way or this way, up, down, down, and I end up back at the same voltage I started at. So let's put a box around that too. This is KVL, Kirchhoff's voltage law. Now I started over here in this corner, but I could start anywhere. If I started at the top and went around clockwise, if I started here, say, I would go minus 5, plus 10, and I'd get the same answer. I'd still get back to 0. If I start here and I go around the other way, the same thing happens. Plus 5 rise, and this is a 10 volt drop. So it works whichever way you go around the loop, and it works for whatever node you start at. That's the essence of Kirchhoff's voltage law. We're going to pair this with the current law, Kirchhoff's current law, and with those two, that's our tools for doing circuit analysis.